Picture this. Your 5-year-old is learning the same logic software engineers use to write code, but there's not a screen in sight. Just wooden blocks, a little robot, and a lot of hands-on problem solving. Sounds too good to be true? It's not. I go by Dr. Priya Mehta, and today we're breaking down exactly what screen-free coding is and why it might be the smartest entry point into STEM learning for your child.
You're listening to the STEM Lab podcast. Quick heads up before we jump in. Everything you're about to hear, the research, the data, the script, all of that's been written and verified by real human authors. The voice delivering it, though, that's AI generated. Just want to keep that transparent from the start. If you've been listening for a while, thank you, seriously. And if you're new here, glad you found us. We drop new episodes every Monday, Wednesday, and Friday, so there's always something fresh to dig into. Let's get into it.
You've probably heard the term screen-free coding floating around in parenting circles, but what does it actually mean? And more importantly, why should you care when your child's future seems so connected to technology? Screen-free coding introduces children to computational thinking and programming logic through tangible, hands-on tools instead of screens. It's a foundational approach that builds problem-solving skills without the eye strain, behavioral concerns, or device dependency that worries so many of us. So let's start with the basics. What is screen-free coding? At its core, it's an educational method that teaches programming concepts like sequencing, loops, conditionals, debugging, and algorithms using physical objects rather than digital devices. Children manipulate tangible pieces, wooden blocks, plastic tiles, fabric cards, or cardboard cards that represent code instructions. This approach, sometimes called unplugged coding or tactile programming, emerged from computer science education research in the 1980s and gained mainstream traction as parents and educators grew increasingly concerned about early childhood screen exposure. The beauty of screen-free coding lies in its simplicity. A child arranges directional arrow cards to guide a robot toy, stacks command blocks to create a sequence, or places instruction tiles on a mat to program a pathway. These tools translate abstract computational concepts into concrete experiences. When your 5-year-old physically moves a wooden forward block next to a turn right block, they're building the same sequential thinking skills used by software engineers writing Python or JavaScript, but they're doing it with their hands, not their eyes locked on a glowing rectangle. The method aligns beautifully with Piaget's concrete operational stage of development, where children ages 2 to 7 learn best through physical manipulation rather than abstract symbols. Research from the American Academy of Pediatrics continues to emphasize the developmental importance of hands-on play in early childhood, making screen-free coding a guilt-free entry point into STEM learning. Now, let's talk about how screen-free coding actually works. Screen-free coding systems typically include 3 components: input tools, which are the coding pieces your child manipulates, processing mechanisms, which determine how those instructions translate to action, and output feedback, which is what happens when the program runs. Input tools vary widely. Some kits use wooden blocks with printed symbols representing commands like move forward, turn left, or repeat. Others employ plastic tiles, magnetic pieces, or fabric cards. Some robots use a handheld remote with directional buttons that children press in sequence to program the robot's movements. No app required. Premium options like coding board games use stackable instruction cards that children arrange in order. The key is that children physically touch, arrange, and rearrange these elements. This tactile engagement activates multiple neural pathways simultaneously: visual processing from seeing the symbols, motor skills from manipulating pieces, spatial reasoning from understanding directional concepts, and working memory from holding a sequence in mind. Processing mechanisms come in 2 forms: analog and embedded. Analog systems rely on the child or a facilitator to execute the code.
Think board games where you follow a sequence of cards manually. Embedded systems contain basic electronics that read the instructions. Some coding robots use color sensors to scan a sequence of tiles. Others have physical buttons that children press in order, storing the sequence in memory. Some wooden board systems use shaped pegs that children insert into slots, then press a button to make the robot follow that path. Output feedback is crucial for learning. When your child's sequence works correctly, the robot reaches its destination, a light turns on, or a physical goal is achieved. When it doesn't work, and this is where the real learning happens, they see the failure immediately and concretely. The robot bumps into a wall. The pathway leads to the wrong destination. This immediate physical feedback loop teaches debugging skills far more intuitively than abstract error messages on a screen. Unlike screen-based programming environments where mistakes generate cryptic text errors, screen-free coding failures are obvious and fixable. Your child doesn't need to read error codes or understand syntax. They can see exactly where their sequence broke down because the robot stopped short or turned the wrong direction. This approach also naturally introduces iterative thinking. Children rarely get the sequence right on the first try. They run their program, watch it fail, identify the problem step, adjust the sequence, and try again. That cycle of hypothesis, test, analyze, and revise mirrors the actual software development process used in professional programming. Moving on to why this matters, the question isn't whether your child should learn coding concepts, it's how and when. What is screen-free coding offering that traditional approaches don't? 3 things: developmentally appropriate timing, executive function development, and screen time balance. First, screen-free coding lets children as young as 3 years old begin building computational thinking skills years before they're ready for actual programming languages or extended screen exposure. The American Academy of Pediatrics recommends minimal screen time for children under 5, yet computational thinking skills benefit from early exposure. Screen-free coding solves this tension beautifully.
Second, the physical manipulation required by these tools strengthens executive function, which encompasses the cognitive processes that control planning, focus, working memory, and task switching. Research in developmental psychology consistently shows that hands-on problem-solving activities build these skills more effectively than passive screen activities. When your child arranges coding blocks, they're not just learning programming logic, they're strengthening the neural circuits that govern impulse control, planning, and flexible thinking. Third, and perhaps most practically, screen-free coding gives you a way to introduce STEM concepts without adding to your family's daily screen time burden. Many of us feel caught between wanting to prepare our children for a technology-driven future and wanting to protect their developing brains and eyes. Screen-free coding offers that rare middle ground. From a career preparation standpoint, these tactile experiences build the foundational logic that transfers directly to text-based programming. The transition from screen-free coding to Scratch and Python becomes seamless because children already understand sequencing, loops, and conditionals at a conceptual level. They simply need to learn the syntax. Let's break down the types of screen-free coding tools available. Screen-free coding tools fall into 4 main categories, each serving different developmental stages and learning objectives. Screen-free coding robots are the most popular category. These battery-powered devices respond to physical programming inputs. Basic models use segmented body pieces that snap together. Each segment represents a command, and the robot follows the sequence when activated. Advanced options include robots that scan color-coded tiles or read sequences from command cards. These tools typically target ages 3 to 8 and require AAA or rechargeable batteries. Most are Bluetooth-free and operate entirely through physical inputs.
Board games and card games translate programming concepts into playful competition. Games like Robot Turtles use cards representing commands. Children play cards to move their turtle across a board, building sequencing and debugging skills through gameplay. These analog options require no power, no connectivity, and zero screen dependency. Pure tactile problem solving. They're ideal for ages 4 to 10 and easily integrate into family game nights. Programming puzzles and manipulatives include wooden block sets, magnetic tiles, and fabric mats with coding challenges. Children follow challenge cards that present a problem, like getting a character from point A to point B, then construct a solution using physical coding pieces. These tools emphasize spatial reasoning and algorithm design. The progression from basic sequencing to complex conditional logic happens naturally as children advance through increasingly difficult challenges.
Unplugged activity books and curriculum kits provide structured lessons using paper-based exercises, physical activities, and craft projects. Children might act out sorting algorithms by arranging themselves in order, or create binary bracelets using beads. These no-cost or low-cost options work well in group settings and require minimal setup. They're particularly effective for ages 6 to 12 who can engage with more abstract pattern recognition. Each category has distinct practical considerations. Robots require battery maintenance and storage for small pieces. Board games need flat workspace and adequate lighting. Manipulative sets benefit from organization systems like labeled bins or storage cases to prevent piece loss. Most quality screen-free coding tools are designed for repeated use. Look for durable materials like hardwood, thick cardboard with laminated surfaces, or high-impact ABS plastic, rather than thin components that crack or bend. Now, let's address some common questions. How is screen-free coding different from regular programming? Screen-free coding teaches programming concepts like sequencing, loops, and conditionals through physical, hands-on tools, such as wooden blocks, coding cards, or programmable robots that operate without screens or apps. Regular programming requires a computer, tablet, or device with a screen interface, and typically involves typing text-based code or using visual programming languages on screen, whereas screen-free coding uses tangible objects your child can touch and rearrange to create instructions. At what age should children start? Children can begin screen-free coding as early as age 3 with simple sequencing toys and directional games that teach basic cause and effect relationships. Ages 4 to 5 are ideal for introducing dedicated screen-free coding robots and board games that teach foundational concepts like step-by-step instructions and pattern recognition. Ages 6 to 8 can handle more complex challenges involving loops, conditionals, and debugging exercises using advanced manipulatives. Do these tools require batteries or subscriptions? Most screen-free coding robots require AA or AAA batteries, occasionally rechargeable batteries, to power motors and sensors, though battery life typically lasts 8 to 12 hours of active use. Board games, card games, and manipulative sets require no power whatsoever and work entirely through physical interaction. The vast majority of screen-free coding tools are one-time purchases with no subscription fees, consumable refills, or app dependencies. You buy it once and use it indefinitely.
How does screen-free coding prepare children for real programming languages? Screen-free coding builds the fundamental computational thinking skills that underpin all programming languages. Sequencing, which is putting instructions in order, debugging, which is finding and fixing mistakes, loops, which are repeating actions, and conditionals, which are if-then logic. When children eventually transition to Scratch, Python, or Arduino, they already understand the logic and structure of programs and only need to learn the syntax and typing mechanics rather than the conceptual foundation. Can these tools be used in group or classroom settings? Screen-free coding tools are exceptionally well-suited for group learning because they encourage collaboration, turn-taking, and peer teaching without the isolation that individual screen time creates.
Most coding robots work perfectly with 2 to 4 children working together to solve challenges. Board games naturally accommodate multiple players, and manipulative sets can be divided among learning stations, making them particularly effective in homeschool co-ops, library programs, and classroom STEM centers, where children can observe each other's problem-solving strategies. To wrap up the main points here, screen-free coding is an opportunity. It's a way to introduce your child to the foundational logic of programming through hands-on, tactile experiences that align with how young brains actually develop. By using physical tools instead of screens, you're building computational thinking skills while respecting the developmental needs of early childhood. These aren't just toys. They're the first steps in a progressive learning path that can lead from wooden blocks at age 3 to Arduino programming in middle school. The best part? You don't have to choose between preparing your child for a tech-driven future and protecting them from excessive screen exposure. Screen-free coding gives you both. Whether you're exploring different kits or planning a complete home STEM lab setup, these tactile tools offer a gentle, developmentally appropriate entry point into one of the most valuable skill sets of the 21st century. No glowing rectangles required.
That wraps up this episode of the STEM Lab podcast. Thanks for listening. We've got new episodes coming out every Monday, Wednesday, and Friday, so there's always more to explore. If you got something useful out of this, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It actually makes a difference. It helps other parents and educators find the show, and that's how we grow this community. And go ahead and hit subscribe or follow so you get a notification the moment a new episode drops. Catch you next time.